For this lesson, the first thing we're going to talk about is how to tell the difference between independent and paired samples, and we'll look at a problem. A drug company has developed a new drug that is designed to reduce high blood pressure. The researchers wish to design a study to compare the effectiveness of the new drug to that of the old drug. Here's one way in which the study can be designed. In this one, 2 samples of individuals are chosen. One sample is given the old drug and the other sample is given the new drug. After several months, blood pressures of the members of both samples are measured. We compare the blood pressures in the first sample to the blood pressures in the second sample to determine which drug is more effective. In this design, the samples are independent. This means that the observations in one sample do not influence the observations in the next. You've got 2 totally separate independent groups. Now, here's another way that the study could be designed. A single group of individuals is chosen. They are given the old drug for a month, then their blood pressures are measured. Then they switch to the new drug for a month, after which their blood pressures are measured again. This produces 2 samples of measurements, the first one from the old drug and the second one from the new drug. We compare the blood pressures in the first sample to the blood pressures in the second sample to determine which drug is more effective. In this design, you've got a single group and the samples are paired. When they are paired, they're not independent because it's the same person or sometimes it's somebody very similar, but most of the time it's the same person. Each observation in one sample can be paired with an observation in the second. Now, pause the video and read these 2 and see what you think they are. All right, and in letter A, I've got a sample of students. I've got one sample. Each takes a reading test before and again after the class. The 2 samples are scored and compared to determine how large an improvement in reading speed occurred. This would be paired. You would be compared to yourself in that. And the second one, I've got a sample of students in an online stats class and another sample in a traditional stats class. So we've got 2 samples. At the end of the semester, the students are given a test. The scores from each sample are compared to determine which class was more effective, and this would be independent. You've got 2 different groups. You're not comparing someone in before and after type scenario. Now, what we're going to do in this lesson is we're going to do independent samples, and we're going to find confidence intervals for the difference between 2 population means. Now, imagine that we will compare a new blood pressure drug to a standard drug. We will draw 2 independent samples. The first will be given the new drug and the second will get the standard. We can imagine these samples as coming from 2 populations, a population of patients who take the new drug and a population of patients who take the standard drug. For each population, there is a mean reduction in blood pressure. We are interested in estimating the difference between the population means. Let mu1 be the population mean reduction for the new drug. Let mu2 be the population mean reduction for the standard. You want to make a confidence interval for the difference. The point estimate for the difference is the difference between the sample means. In other words, the point estimate is your sample means, the difference, x bar 1 minus x bar 2. And remember when we did a confidence interval, we got the point estimate, and then we had that plus or minus, that margin of error. And that's what we will do today, except your calculator is going to figure out the margin of error. You won't have to do the math. And when we have 2 independent tests, we use what's called Welch's method, and you've got 3 assumptions instead of 2. And here are the 3 assumptions. The first one's the same old thing, an SRS from both samples. The new one is that the samples are independent. And the third one is our normal condition again. Either the sample is large, n is greater than 30, or the populations are approximately normal, or you're going to examine your data. And if you do that, you're going to make a graph like what we did before. All right, pause the video and read over this problem, please. Now notice in this problem that you've got two samples, one that's taken the new drug and one that's taken the standard drug. Notice that it gives you this standard deviation. That is not sigma. That's not population standard deviation. So this is going to be a T interval, and it's going to be what's called a 2-sample T interval. And when you do your screenshots, for now on, you need to put whether it's 1 sample or 2 samples, because we do have 2. Now, here's what I want you to do. When you check your conditions, the first thing is SRS, and you just say both groups. They are independent, and they're independent because you did not have matched pairs. And the third one, the normal condition, it's said in the problem that they're approximately normally distributed. So I can say normal, both. Okay, and that's perfect. Now, what I'm going to do for this problem, and you need to be careful how you subtract, and you always want a difference in these. I want the population mean reduction for the new drug and the standard drug. So what I'm going to do is I'm going to do new drug minus standard drug. And what I'm going to write in red, you do not have to write. I'm going to write it for these two, but when you're doing your papers and your ALEKS, I don't think you need to write this. But here's what I want for the new drug. I want my X bar 1. I want my S of 1. I want my N of 1. And ultimately, I want to know what's the mean of this new drug if I switch all my patients to the new drug. The standard drug, I want my X bar 2, my S of 2, my N of 2, and ultimately my mu of 2. And like I said, keep in mind we're finding a difference. Now, the new drug, I've got to look back in your problem, a sample of 15 patients on the new drug. Their systolic blood pressures are reduced by an average of 28.3 with a standard deviation of 12. The standard drug, I had 20 patients taking the standard drug. The blood pressures in this group are reduced by 17.1, and the standard deviation is 9. Now, if you look at the two drugs and you look at the difference, I'm going to write this up here. With our sample, okay, so if I'm looking at the sample, my new drug was 28.3. My standard drug was 17.1. If you go to your calculator and you do 28.3 minus 17.1, I can see that the new drug is better because it reduced it by 11.2 milligrams of mercury more than the standard drug did. So based on my sample, the new drug is better. But I need to figure out, okay, what happens with the population? And that's where your margin of error comes in. Remember when we talked about our other problems and we would say, like in an election, someone had 48% of the vote plus or minus 5? That margin of error makes a big difference, and that's what we need to find out. So here's my my point estimate, 11.2, but what's my margin of error? And on your calculator, you're going to go to inference, and I'm going to go to intervals. What we've talked about, we don't do the proportions. This is not one mean. This is not two proportions. This is two means. And it's going to be a T interval because I don't know sigma. And I'm going to input my statistics. And then it's going to have you enter the data. So my X bar 1 is 28.3. My S of 1 is 12. My N of 1 is 15. My X bar 2 is 17.1. My S of 2 is 9. My N of 2 is 20. And I'm doing 95% confidence. And you're going to just keep going to next. All right, once you get to here, now I want you to look at what it gives you. There's your point estimate, that 11.2, what we talked about. Notice it gives us some more information that we don't need. I want to go to next. And here it gives me that 11.2 and that margin of error, that plus or minus. The margin of error is 7.6088. Now, here's how I'm going to list my answer. Here's how I'm going to do my screenshot. I'm going to say we did a 2-sample T. And I'm going to put my 11.2 plus or minus my margin of error. And then I'm going to list my confidence interval like we listed on our paper, 3.5912 to 18.8088. And you can list that however you want. But now here's going to be my conclusion. So I'm going to say we are 95% confident that the true mean, you could either say reduction or difference. The true mean reduction, I'm going to put difference in parentheses. You don't need both. The true mean reduction in blood pressure is between our 3.5912 mmHgs and 18.8088 mmHgs. And the big thing you need to understand here is this is telling me that the new drug is better. Now, how can I tell? Because I have a positive confidence interval for the difference. Okay, so positive difference means that the new drug had to be higher than the standard drug. The new drug is better. I have a positive confidence interval. Pause the video, please, and read your problems. Once you do, you'll see that this is another 2-sample T interval. And we're going to start with checking our conditions. And first is I have a SRS both. The two groups are independent because it didn't say that they tagged the flounder and measured them at 1-year-old at 1 and 2. It's two independent groups. The problem didn't say normal or I would say normal, both check. But I can use CLT for both. So N is greater than 30. CLT tells me normal for both. All right, now what I want to do is I want the mean difference between 2 and 1-year-old flounder. So what I want is 2-year-old minus the 1-year-old. And what I'm going to do, and this is a part that you don't have to write, I'm going to look for my X bar 1, my S of 1, my N of 1, and ultimately my mu of 1. And the same thing over here, X bar 2, S of 2, N of 2, and mu of 2. All right, so if you look at the problem, I had 87 1-year-old flounder, had a mean length of 126.31, and the standard deviation was 18.10. I had 132 2-year-olds. Mean length was 162.41, and the standard deviation was 28.49. Now, I want you to look at your sample to start with. All right, so here's my sample. My 2-year-olds were 162.41. And my 1-year-olds were 126.31. All right, and here's what I know from my sample. My 2-year-olds were longer. How much longer? 36.1 millimeters. How do I know that they were longer? Because I subtracted them and I got a positive difference. So the first number had to be bigger. The 2-year-olds were longer. Now, the question is, what's that margin of error for the population when I come up with the confidence interval? So 36.1 plus or minus what? And that's what we're going to use the calculator for. You don't have to do any math, so don't go to distributions. Go right to inference. I'm going to do an interval, and I'm going to do two means. I'm going to do a t-interval. We do not do the pooled t-interval. I forgot to mention that on the last one, but you don't do the pooled. I'm going to do the t-interval. I'm going to input statistics. My first sample mean is 162.41. My S is 28.49. My N is 132. The second one is 126.31, 18.10, and 87. I want 95% confidence. There's that point estimate, that 36.1. I'm going to skip this, and I'm going to go to my answer. And here's how I'm going to list my answer. I think this is the best way to list it, but that's up to you. I did a 2-sample T. And I'm going to do my 36.1 plus or minus my margin of error. And then I'm going to list it just like we list it in our paper. It's 29.8939 and 42.3061. All right. And here's what I'm going to give as my conclusion. I'm going to say we are 95% confident that the true mean difference, now this time you got true mean because you want population mean and you're taking a difference. That's the difference of the two samples, just like when we talked about that 36.1. The true mean difference is between 29.8939 and 42.3061 millimeters. You could do better because you could talk more about, you could mention the 2-year-olds and 1-year-olds, but that would be enough. But what I want you to know is that the 2-year-olds are longer. All right, how much? Between 29.8939 and 42.3061 millimeters. How do I know they're longer? Because I have a completely positive confidence interval. And that's what we're going to talk about in our last thing. What kind of conclusions can I make from these confidence intervals? Now, here's what, we're going to pretend this, but I want to show you something. Say that I did a confidence interval for SU minus UMES males, and I did heights, and I did a 95% confidence interval. Now look what I did. I did SU minus UMES, and say that I got this as an answer, 2.5, 3.7. So I got my my point estimate. I did my margin of error. This is what I got for my confidence interval. Now, I did SU minus UMES. I got a positive interval. This means that SU is taller between 2.5 and 3.7 inches. That's what that means. Now, say I did not get that. Say I got this. Now look what I got. I got both numbers are negative, and I did SU minus UMES. So to get the negative, UMES has to be bigger. Okay, UMES has to be taller. So here's what happens here. UMES is taller between 2.6 and 4.8 inches. Now, I don't think I would get either of them because you know what I think about heights. What I think I would get for height is some kind of interval that went from a negative number to a positive number. Now, it probably wouldn't go that nicely. The numbers probably would not be that nice. But I think I'd have negative and I'd have a positive. Now, when you're looking at a number line and you go from negative to a positive, 0 is included. And if you have a difference of 0, it means no difference. Like my SU height was 5'9", my UMES height was 5'9". 5'9" minus 5'9" is 0. All right, so if you go from negative to positive, it's no difference. And the easiest way to explain that is because 0 is in the interval.